at a volume of these. And what I'm going to do is I might find the relationship between these points and say the little local normals associated with the point, or something to do about the geometry. The idea is whatever it is that I'm measuring is not a function of how I looked at the points. So in fact, the way we often do these is we typically will build we'll take these points and we'll build a description, and we'll put them into a histogram. Okay, so maybe we just quantize these different orientations into, 5 different levels. So we have, 5 level thing, and then we might have distances. So in fact, one example, they used a 5 by 5 by 5 histogram that gave you 125 different values. Okay, remember in SIFT, I think we had 128 different values. So here we have 125 different values. And then for every patch, we compute these, and we can compare them against the patches in our model, find the putative matches, and then do something like ransack to do the matching. There's a version called the fast point feature histogram, which is a way of doing this in 3D. And again, I think is probably implemented directly in the point cloud library. So there are a couple of places where the point cloud library, I already pointed you at pointclouds.org. For many of you in the robotics universe, there's something called ROS, the Robot Operating System, originally out of Willow Garage, and then it's Robotic Software Open Foundation. It's got all those letters in it. It's an open source ongoing development system for doing robotics. And the point cloud library, and by the way, OpenCV, computer vision library, are all part of that universe. And that's really helped make it easy for people to do that development. And there are drivers, by the way, in that for using the Connect or PrimeSense sensors as well, so you can go get your point clouds that way. So here's a picture that I showed you before from pointclouds.org. And in fact, here it says ransack cylinder segmentation. So basically, they ransack to find the different planes and to also find these different cylinders. You know how to do that already, so you could do this. And it basically gives you a direct interpretation of the geometry. So that ends our discussion on direct depth sensing. Probably 6-7 years ago, I wouldn't have even mentioned it anymore because light striping was sort of relegated to sort of assembly line machine vision. But with the advent of the Kinect and other types of such sensors, and really robotics putting geometry back as a first-class computer vision problem, depth sensing has become a big deal again. And since many of the manipulations are similar to what we do with images, it made sense to consider it within computer vision. Good morning, or whatever time it is by you. Welcome back to Computer Vision. This is our last general unit for computer vision. And it's actually, we're going to talk about what's probably the most remarkable vision system in the world, namely the human vision system. And that's just not me being sort of arrogant about us as a species, but we really do have a remarkably well-developed visual system. We'll talk about sort of how much of the brain that makes use of it, especially at high-level kinds of structures. So the brain is generally what we're talking about, and here you have a picture, the overall view of the human brain. A friend of mine, Jeremy Wolf, always said, make sure you draw on the nose. So, okay, so your nose is over there, your eyeball's here, and then there are all these various structures, the cerebellum in the back of your behind your head is where a lot of rapid motor control kinds of things take effect, whole bunch of structures. All of this crinkly stuff up here is the cortex, and we'll talk about that a little bit later. By the way, these little things sticking out right here called the olfactory bulbs, those are the things that actually go into your nasal cavity that does sense of smell. That's actually a part of your brain that sticks out into your nose. And another part of your brain that sticks out is actually your retina, and we'll talk about that in a minute. The parts of the brain I want to talk about today are, this lesson and next, of course, are the parts that are involved with the human vision system. And those are poorly drawn here on this schematic. It's just ugly, but it's actually much clearer. So again, here we have your two eyes. Okay, again, now your nose is up here. And you'll notice that coming out of each eye is what's referred to as an optic nerve, and they sort of cross in this funny way at what's referred to as the optic chiasm. They then make a way stop. They make a stop here, down in here, in the lateral geniculate, and then the lateral, which we'll talk about, and the lateral geniculate has projections up into something called the superior colliculus, and a lot of it goes to what's called the visual cortex. And we're going to talk about that. By the way, we describe these things as if it's a flow of information going up. And that's partially because as computationalists, we like to say, well, first we do some low-level processing at the detectors and the retina, and then it goes up to these way stations where various kinds of things happen, and then up for higher level processing. The reality is somewhere between 80 and 95% of the projections into, for example, the lateral geniculate are actually from the cortex back down. So the engineers amongst you will say, oh, that's got to be feedback of some sort. Well, indeed, it probably is, and it's still stuff that we're just slowly getting a handle on. So take what I'm about to say with a grain of salt. In fact, well, take everything I ever say with a grain of salt, but in particular, I'm only going to give you a relatively simplistic view of what's going on in the vision system. It's also a slightly dated view because while I'm try to be pretty current about certain computer vision things, there's a massive, massive field of neurophysiology and human vision, so I'm just going to give you some of the highlights. And it'll give you a general overview, and I encourage you to read more as we go forward. One thing to say also before we continue forward is sort of the anatomy and physiology of the brain really reflect the computational complexity of vision. So to give you an example, you have auditory nerves that come from your cochlea that go into your brain, and those nerves, there's two of them, one for each ear, and those nerves have somewhere around 30,000 nerve fibers in that bundle, okay? The optic nerve, each one coming out of here, that has somewhere around 1 million fibers, okay? 30,000 for hearing, 1 million for vision from each. Likewise, and we'll talk more about this later, we're going to talk about visual cortex, this area back here. So far, you can, again, plus or minus, somewhere around 30% of your cortex, right? The cortex being the most recent part of the brain in terms of evolutionary structures, and we think of it as being the sort of the human element. Somewhere around 30% of the cortex is seen to have something to do with vision, as opposed to, say, 3% for hearing and 8% for all somatosensory touch. So again, the complexity of vision is not only showing up when you look at your problem sets and you say, how could this possibly work, but is also reflected in the detailed structure of the human anatomy. So let's talk a little bit about vision in your visual field. So as you know, you've got two eyes. Well, you start out with two eyes for most of us. Each eye is about 160 degrees, and they overlap at about 120 degrees, which means if you do the math, it means you have about 200 degrees total field of view. Different animals are different, by the way. Some animals, the ones that are prey as opposed to predator, their eyes are back here, so they have a wider field of view. That is, they can see more further behind them, which you might want to do if you're worried about a predator. But of course, it means you have less stereo vision. But remember, we were talking about nerves coming out and crossing this area called the optic chiasm. Let's take a look at that a little more carefully. The human vision system does, well, you're probably quite familiar with your motor control system, right? That the left part of your brain controls the right arm and the right part of your brain controls the left. And if you have a stroke on the left side of your brain, you'll lose some motor function, also some sensory function. Well, you probably didn't stop to think about that the eyes have a tricky problem, right? So the stuff that I see over here is seen in this eye and in this eye. And the stuff I see over here is seen in this eye and in that eye. How does the brain deal with that? Well, the way it does it is it actually splits the eyeball in half in terms of where the projections come from. So here we see the right visual field, which is looked at by this left side of the eye, which is the temporal side of the left eye and the nasal side of the right eye. Though both of those come in through the optic chiasm, going to the left side of your brain. So the left side of your brain is looking at the stuff over here on the right in both of the eyes, okay? And likewise, the right side of my right eye and the right side of my left eye, which is looking at the stuff on the left-hand side, is projected to the right-hand side of my brain. And so just the same way that your sensation on your right arm is in your left brain, the sensation in your right visual field is at your left brain. Also, in this other view of the sort of the projection of the optic system into the brain, you can see these other structures, right? So we get here to the lateral geniculate, again on both sides, projecting the superior colliculus. And here you can see that there are these projections out to this whole area of visual cortex, which is in the back. And we'll look at that. One of the implications of this right half, left half, right part of your brain looking at the left half, vice versa, is if you have a some sort of degeneracy or stroke or something, and let's say you were to lose some function in one side of your brain, you would experience what's referred to as, here's written, hemifield neglect. Okay, and what that means is that, so if you had damage, let's say, to your left side of your brain, the whole right side of your area would just sort of not be there. And what's interesting, and we'll see an example of this in a minute when we talk about blind spots and stuff, you don't feel like there's a hole there. You just feel like this is my field of view. I don't actually know what's over there. Okay, so it's not like right now I feel there's a hole back here, despite what my wife says, there's no hole in the back of my head, I don't think. But I just know that I can't see what's back there. Well, what happens is if your brain sort of starts not knowing what's over here, it just kind of, just doesn't worry about it. And in fact, what will happen is it'll fill in some stuff for a little bit, kind of like you do with the rest of your visual field. We'll talk about that in a minute too. But I don't want you to get a sense that you would feel like there was a great big black hole sitting over there. All right, so let's start sort of climbing up the visual system, starting at the bottom, which of course is the eye. And here's a sort of a schematic picture of the eye, and light's coming in this way. And there are a variety of structures. Let's see, a couple that we'll mention. So you have this lens here. Lens changes what's in focus. And by the way, you have what might be thought of as a spherical retina. And so in some sense, spherical retinas are a lot easier to deal with planar retinas. We put planar retinas in cameras and things like that. Spherical means all the rays are sort of the same, which is kind of nice. The other thing to notice on these lenses is that they're attached by these fibers right here. And those fibers pull on the lens, and they cause the lens to deform, which changes the focus, and that's how you focus near and far. Well, that's how you focus near and far. The way I focus near and far is I put on reading glasses. Why is that? Because I'm old. Well, I'm not that old, but what happens is my eyeballs think I'm old. In fact, sometime right around my 40th birthday, I looked at my watch, and I was trying to wonder how my watch knew it was my 40th birthday because it decided to go out of focus just that day. But what happens is the ability of your those fibers to deform that lens, it hardens up a bit, and you lose the ability to deform the lens as much, and you can't do near focus. And that's why you see those of us with less hair carrying around reading glasses. So the lens focuses the light coming in, goes through this center area called the pupil. You have a certain amount of adjustment of the size of the pupil in terms of the amount of light that's in there. We'll talk about the dynamic range in a minute. And then what happens is the light passes through a clear liquid, which keeps the eye in its shape, and it projects onto this back area called the retina. Okay? And one of the things you'll also notice in here is that there's this optic nerve. There's also a bunch of blood vessels that come in and feed the retina. And we'll talk in a little bit about how come it is that it comes all the way up through here so that it actually sees the middle here. That is, it's not just in the back. But when you look in there, what you would see is a funny little area. It's referred to as the optic disc or the blind spot. And in fact, if you've ever been to an ophthalmologist and he looks in your eye, what he sees is something like this. All right? That's assuming everything's healthy. So there are all these blood vessels that are nurturing the retina. And then there's this area in the middle where the blood vessels and the nerves are coming together. And that's your blind spot. So how many people would like to find their blind spot? Raise your hand. You can't. It's blind. No. We're going to do that. So it's actually really, really easy. A couple of ways that we can do this. So on my screen right now, I have a picture of a plus and a dot. Your blind spot is always on the outside of your visual field. So what I'm going to do is I'm going to look for the blind spot in my left eye. So it's going to be outside. So what I'm going to do is I'm going to, whoa, it happened right now. So right now I'm looking at that dot on the right, and to the left of it is a cross. And if I move here, there's the cross, but right here, the cross is gone. I think that's at 12 degrees. I can't remember. I think it's 12 degrees out, right? It's just not there. It's just plain black. Okay, if I want to do it with my right eye, well, what I'll do is I'll look at the cross, and I'll move until there it goes, the circle is gone. If you are doing this, if you rotate your head like that, the cross comes back because the blind spot is located off to one side, and as I rotate, the blind spot is now up here, and the cross pops back. in class, normally what I do is I make a bunch of pieces of paper and I hand this out right here, okay? And I ask people to take their left eye. So for those of you not paying attention, so we have a dot, and over here we have a bar with a crosshatch pattern in the